Tonight, we're going to look at what it would actually take for a real Starship to survive in deep space. Not just survive the launch or the first year, but survive the full thing. Decades of continuous operation in an environment that is hostile in ways that don't get better with distance. People talk about interstellar travel as an engineering challenge. It is, but it's an engineering challenge that has to keep working, without help, without replacement parts, and without a second chance, for longer than most machines we've ever built have existed. And building the ship is only the beginning, because the moment it leaves, everything out there starts working against it. By the end of tonight, you're going to understand exactly which systems fail first, which ones outlast everything else, and how long a genuine Starship could actually keep itself alive. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Engineers can't simply wait 50 years to find out whether a component will survive 50 years. So much of what we know about long-term spacecraft durability comes from a technique called accelerated life testing. It means deliberately exposing materials and components to intensified versions of the stresses they'll face in space, compressed into a far shorter time frame. A seal that will experience several thousand thermal cycles over a real multi-decade mission might be cycled through that same number of temperature swings in a matter of weeks inside a specialized test chamber. That lets engineers observe how it degrades without literally waiting decades to find out. Radiation effects get tested similarly. Particle accelerators and radiation sources here on Earth can deliver, in hours or days, the same cumulative dose a spacecraft component might absorb over years in deep space. This approach isn't perfect. It relies on assumptions about how damage accumulates, assumptions that don't always hold true at extreme timescales. It can also miss slower, more subtle failure modes that only emerge after genuinely long exposure. But it's the primary tool engineers actually have for predicting how a Starship's components might behave decades or centuries into a mission that hasn't happened yet. It's also part of why organizations like NASA maintain dedicated testing facilities built specifically to simulate the vacuum, temperature extremes, and radiation environment of deep space as closely as current technology allows. A quick clarification helps here, since science fiction often muddies this particular point. At 15 or even 20% of the speed of light, a real Starship would experience only a very slight degree of time dilation. That's the effect where time passes more slowly for a fast-moving traveler relative to someone who stayed behind, described by Einstein's special relativity. The effect becomes dramatic, only much closer to the speed of light itself. At 20% of light speed, roughly 37,256 miles per second, the difference is small. Time experienced aboard the ship and time experienced back on Earth would only differ by a few percent across the whole voyage. That's meaningful for precise scientific timing, but nowhere near the dramatic decades-long discrepancies often depicted in fiction. This matters for our purposes tonight. It means the aging and wear processes we've been discussing all unfold at essentially the same rate aboard the ship as they would for an equivalent system sitting still. Radiation damage, mechanical fatigue, power decay, all of it at the same pace. There's no meaningful relativistic slowdown to buy the crew or the hardware extra time. Start with what we actually mean by a Starship. Not a fantasy vessel bending space around itself. Not a ship that ignores the speed of light. A real starship, the kind serious engineers have actually designed on paper, is something closer to a city built inside a tube of metal and ceramic. It rides a column of controlled explosions or a beam of superheated plasma toward a star that might be 4, 10, or 20 light-years away. The stakes of getting this right are considerably higher than they are for a typical robotic mission closer to home. A rover on Mars that develops a mechanical fault can often be worked around with software patches sent from Earth, since the round-trip communication delay is only a matter of minutes. A satellite in Earth orbit experiencing a serious hardware failure can sometimes be visited and repaired by astronauts, as happened repeatedly with the Hubble Space Telescope. A Starship, years or decades into an interstellar crossing, has neither option available to it. Whatever fails, fails permanently, unless the ship itself carries the capability to diagnose and fix the problem entirely on its own, using only what it brought with it. That single constraint, the complete absence of any outside help for the entire duration of the mission, is really what elevates every one of the engineering challenges we've discussed tonight. It turns a routine spacecraft design problem into something considerably more demanding. This isn't purely an academic exercise, either. Organizations, including the British Interplanetary Society, produced the detailed 1970s-era Daedalus study. Icarus Interstellar later revisited and updated much of that same work decades afterward, under a project called Icarus. Both have spent thousands of collective engineering hours working through exactly these trade-offs on paper, refining propulsion concepts, shielding requirements, and mission timelines, using the best available physics at each point in time. NASA itself has periodically funded smaller-scale studies into interstellar precursor missions and long-duration spacecraft reliability. That includes work connected to the Breakthrough Starshot initiative, which brought together astrophysicists and aerospace engineers. Their goal was to study what a minimal, fast, laser-propelled probe would need to survive its journey to Alpha Centauri. None of these organizations claim to have solved every problem we've discussed tonight. What their decades of combined work have established is that the challenge is well-defined and extensively studied. It's grounded in real, testable engineering. The actual hardware needed to attempt a real interstellar voyage remains, for now, still years or decades away from being built. Concepts like Orion, which used small nuclear detonations to push a pusher plate forward in stages. Concepts like Daedalus, designed by the British Interplanetary Society in the 1970s, which would have used fusion pellets ignited by electron beams. Concepts like fusion ramjets, antimatter-catalyzed engines, and enormous solar sails pushed by lasers fired from our own solar system. None of these exist yet. But all of them are grounded in physics we already understand, not physics we're hoping to discover. And that distinction matters. It means every one of these designs is bound by the same unforgiving rules that govern every machine humans have ever built. Rules about fatigue, rules about corrosion, rules about radiation damage, rules about the slow, patient decay of anything left alone long enough. The Orion concept, in particular, offers a useful early lesson in this kind of long-term wear, even though it was designed decades ago and never flew. Its pusher plate, a massive steel disc positioned at the rear of the ship, was meant to absorb the force of hundreds or thousands of small nuclear detonations set off one after another. Each explosion vaporized a thin, sacrificial coating on the plate's surface, transferring momentum through a shock-absorbing system to the rest of the ship. Engineers, working on the original Orion project, in the 1950s and 60s, calculated that the plate itself would slowly erode with every detonation, losing a measurable layer of material each time. That meant the entire propulsion concept was built around the assumption of gradual, planned material loss, rather than a single component expected to last untouched for the whole mission. It's a useful illustration of a broader principle that shows up again and again in real Starship engineering. Sometimes the answer to long-term survival isn't preventing wear entirely. It's designing a system that expects to wear down in a predictable, controlled way. It carries enough margin, enough spare thickness, enough redundancy to keep functioning until the mission is complete. A Starship built this way would need to survive a journey lasting decades at minimum, and depending on the destination and the propulsion method, potentially centuries. That single fact changes everything about how we need to think about survival. This isn't about surviving a launch, or a landing, or even a few years in orbit. This is about a machine holding itself together across a timescale longer than most human institutions have ever lasted. Longer than most buildings stand before they're demolished or rebuilt. And it has to do this while completely alone. No chance of resupply. No repair crew waiting nearby. No way to simply pull over and wait for help. To put the scale in perspective, the nearest star system to our own, Alpha Centauri, sits about 26 trillion miles away. Light itself takes roughly 4.37 years to cross that distance. Even a ship capable of reaching 15% of the speed of light, faster than anything humanity has ever built by an enormous margin, would still need close to 30 years just to make that crossing. And Alpha Centauri happens to be about as close as any other star gets to our own. Reaching most other nearby systems, places like Barnard's Star or Tau Ceti, would take considerably longer given the propulsion technology realistically available in the coming century. Every one of those extra years in transit is another year every system on the ship has to keep working without failure. Another year of radiation exposure. Another year of dust erosion. Another year of slowly declining power output. The first thing working against a Starship is the vacuum itself. Not in the dramatic way people imagine, with hulls exploding outward in an instant. Real vacuum failure is slower, quieter, and in some ways more dangerous because it's so easy to miss. Every seal, every gasket, every joint between two pieces of metal is a potential leak point. On Earth, a small leak in a pressurized container is an inconvenience. In deep space, over a journey lasting decades, that same tiny leak becomes a countdown. Materials that seem solid at room temperature slowly outgas in a vacuum, releasing trapped molecules of moisture, solvents, or trapped air that were locked inside during manufacturing. Over months, this is negligible. Over decades, it adds up into a measurable loss of pressure. It becomes a measurable degradation of seals that were never designed to hold for that long. Rubber and polymer seals are especially vulnerable. Most rubber compounds become brittle when repeatedly exposed to the extreme cold of deep space, then expand again when warmed by onboard systems or occasional exposure to sunlight. This cycle, repeated thousands of times across a multi-decade voyage, causes microscopic cracking. Each crack is a new potential leak path. Engineers can mitigate this with metal-to-metal seals, welded joints, and redundant pressure boundaries. But redundancy only buys time. It doesn't eliminate the underlying problem. Every additional decade in transit adds more thermal cycles, more stress, more opportunities for a seal that worked perfectly for the first 30 years to finally fail in year 40. Then, there's the erosion problem. And this one is almost never discussed outside of engineering papers. Interstellar space isn't perfectly empty. It contains a thin scattering of gas and dust, mostly hydrogen atoms, with occasional larger grains of interstellar dust left over from dying stars. At normal speeds, this dust is harmless, a whisper of matter so thin it would take enormous stretches of time to matter at all. But a real starship isn't traveling at normal speeds. To reach another star system within a human lifetime, or even within a few generations, it needs to move at a meaningful fraction of the speed of light. That's somewhere in the range of 10 to 20% of light speed for the more ambitious fusion and antimatter concepts. At those velocities, a single hydrogen atom striking the hull carries the kinetic energy of a tiny bullet. Multiply that by the sheer number of atoms a ship encounters every second of a decades-long cruise, and you get a slow, grinding, sandblasting effect on the leading edge of the hull. This is one of the most serious, unsolved problems in interstellar ship design. A forward shield could handle this. It's sometimes proposed as a thick layer of ice, beryllium, or graphite, positioned ahead of the main hull. It would need to absorb this bombardment for the entire cruise phase of the mission. Even a few grams of interstellar dust, encountered at a meaningful fraction of light speed, releases energy comparable to a small explosive charge. Engineers who have studied this problem, including those working on the breakthrough Starship concept for tiny laser-propelled probes, have run the numbers. A shield several inches thick might be required just to survive a journey to the nearest star system without being ground down to nothing. And that shield itself adds mass. That changes the fuel requirements. That changes the entire design of the ship. Every solution to this problem creates new problems elsewhere. To understand just how serious this dust problem is, it helps to look at the actual numbers engineers work with when they model it. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter on average, an almost unimaginably thin scattering of matter. At rest, that atom is essentially harmless. But kinetic energy scales with the square of velocity. That means doubling a ship's speed doesn't double the danger from a dust impact. It quadruples it. A starship cruising at even 10% of the speed of light, roughly 18,600 miles per second, turns every microscopic dust grain it encounters into a projectile. Each one carries the destructive potential of a rifle round. At 20% of light speed, that same grain carries roughly 4 times the energy. Engineers studying the breakthrough Starship concept, which proposes accelerating gram-scale probes to around 20% of light speed using ground-based lasers, have had to seriously grapple with this problem. A spacecraft that light offers almost no material to absorb impacts before something critical gets punctured. Their proposed solution involves a leading shield made of dense material like copper or beryllium, oriented to take the brunt of every impact. It sacrifices a small amount of shield material with every collision so the payload behind it stays intact. This is sometimes called an ablative shield, a shield designed to slowly erode on purpose, giving up material a little at a time so the ship underneath doesn't have to. This isn't a purely theoretical concern either. In 2022, the James Webb Space Telescope was struck by a micrometeoroid larger than engineers had modeled for in their pre-launch risk assessments. The telescope sits nearly 1 million miles from Earth and is far better protected than any interstellar starship would be. It left a small but measurable and permanent effect on one segment of its primary mirror. The telescope continues to operate well within its science requirements. Engineers adjusted their long-term degradation models afterward to better account for impacts of that size. But the event was a clear reminder that even careful statistical modeling of space debris can underestimate the real environment. Any spacecraft spending years or decades exposed to it needs margin built in for surprises. The models didn't fully predict. A Starship crosses the genuinely dust-filled expanse of interstellar space, not the comparatively cleaner environment near Earth. It would need to assume impacts considerably more frequent and potentially more severe than anything JWST has experienced so far. Larger, more massive starships face the same physics, but at a different scale. A crewed vessel massing tens of thousands of tons can afford a much thicker forward shield, sometimes proposed as a wall of water, ice, or packed regolith several feet thick. It doubles as both impact protection and radiation shielding at the same time. Water, in particular, is attractive to mission designers because it serves double duty. It absorbs kinetic impacts from dust, while also being rich in hydrogen atoms, which happen to be extremely effective at blocking high-energy cosmic radiation. The trade-off, as always, is mass. A shield thick enough to reliably survive a 50-year cruise through the interstellar medium could weigh more than every other system on the ship combined. That's part of why so many serious mission studies keep circling back to slower, heavier, more heavily shielded designs rather than fast, lightweight ones. Slower ships mean longer voyages, though, and therefore more total decades of wear on every other system. The numbers involved become clearer once you actually run them. Picture a ship with a leading cross-section of roughly 1,000 square feet, cruising at 15% of light speed on a 4-light-year voyage. Over that trip, it would sweep through a volume of interstellar space containing an enormous number of individual hydrogen atoms and occasional larger dust grains. That's true, even at the famously thin density of the interstellar medium. Most of those encounters involve individual atoms, each one harmless on its own, but collectively responsible for a slow, continuous ablation of whatever material sits at the very front of the ship. The rarer, but far more dangerous encounters involve larger dust grains, particles perhaps a few thousandths of an inch across, which occur far less frequently, but release proportionally far more energy on impact. Mission planners studying these numbers generally conclude that the smaller, constant erosion from individual atoms is a manageable, predictable engineering problem. It's solvable with a sacrificial shield, material chosen specifically to erode slowly and evenly. The larger, rarer dust grain impacts are the ones that actually worry engineers, precisely because they're less predictable. A single unlucky impact from a slightly larger than average grain could, in principle, punch through a shield designed around statistical averages rather than worst-case events. Spacecraft engineers already use a real, flight-proven version of this layered shielding idea, called a Whipple shield, named after the astronomer who first proposed it in the 1940s. Rather than relying on a single thick wall to stop an impact, a Whipple shield uses a thin outer layer positioned a short distance away from the main hull. When a small particle strikes that outer layer, it shatters into a spray of much smaller, lower energy fragments spread across a wider area. The main hull behind it can then absorb that spray far more easily than it could have absorbed the original single particle. This exact approach protects the International Space Station today against the millimeter-scale orbital debris and micrometeoroids it regularly encounters in low Earth orbit. A Starship crossing interstellar space would almost certainly use a similar layered approach for its forward shielding, likely combined with the thick water or ice layer discussed earlier. That creates a multi-stage defense. Each layer is designed to handle a different scale of impact, from the constant, fine sandblasting of individual atoms to the rarer, far more dangerous strikes from larger dust grains. Because that leading shield is expected to erode gradually and predictably rather than fail suddenly, mission engineers would need to treat its remaining thickness as one of the most closely monitored numbers on the entire ship. It's similar to how a submarine crew tracks remaining hull integrity or a mountaineer tracks remaining oxygen. Sensors, embedded at different depths within the shield material, could measure exactly how much protective material remains at any given point in the voyage. That would let the ship, or its crew, calculate with reasonable confidence whether the shield will still provide adequate protection by the time the ship reaches its destination. It would also flag whether the erosion rate has run ahead of projections, so additional material can be manufactured and added before the margin runs out entirely. It's a slow, quiet form of bookkeeping. But on a voyage where the wrong dust grain at the wrong moment could be catastrophic, it's exactly the kind of unglamorous, continuous monitoring that separates a ship that arrives intact from one that doesn't. Radiation is the next major threat, and it's arguably more dangerous to the ship's systems than to any potential crew. Deep space is bathed in galactic cosmic rays, high-energy particles accelerated to enormous speeds by distant supernova remnants and other violent cosmic events. These particles don't just damage biological tissue. They damage electronics. They damage structural materials at the atomic level. They do it continuously, every single day of a multi-decade voyage. A single cosmic ray striking a computer chip can flip a bit, corrupting data or commands in a phenomenon engineers call a single event upset. On Earth or in low orbit, this happens occasionally and can usually be corrected with redundant systems and error-checking code. In deep space, far from the partial protection offered by a planet's magnetic field, the rate of these events climbs substantially. A ship's computer systems would need triple or quadruple redundancy, radiation-hardened components, and constant self-checking routines just to remain reliable across a journey lasting generations. Some Starship designers have proposed a somewhat counterintuitive backup for exactly this reason. They deliberately include simple, mechanical, or analog backup systems alongside sophisticated digital electronics. A purely mechanical system, a spring-loaded valve, or a simple gyroscope is often far more resistant to cosmic radiation than a modern computer chip built from densely packed transistors only a few atoms across. A digital control system might be faster, lighter, and more capable under normal circumstances. But a spacecraft facing decades of continuous radiation exposure benefits from having at least some critical functions, like emergency life support activation or basic attitude control, that don't depend entirely on electronics. Those electronics could, in principle, all fail simultaneously if a sufficiently intense and unlucky radiation event struck the ship at the wrong moment. It's a philosophy borrowed partly from nuclear submarine design here on Earth, where critical safety systems are often deliberately kept simple and mechanical rather than software dependent. Simplicity itself is a form of reliability when the consequences of failure are severe enough and help is far enough away. Navigation presents its own long-term puzzle, one that gets stranger the farther a ship travels from home. Near Earth, spacecraft can navigate using a combination of star trackers and radio ranging signals. Star trackers identify the ship's orientation by comparing what its cameras see against a stored map of bright stars. Radio ranging signals come from Earth itself. Deep in interstellar space, radio ranging from Earth becomes far less useful since the round-trip signal delay stretches into years and the signal itself grows fainter with every additional light year of distance. Star trackers still work in principle, but even the positions of nearby stars shift slightly over a voyage lasting decades, an effect called proper motion. That means a navigation system calibrated for the star field at launch would need periodic recalibration to remain accurate by the time the ship approaches its destination decades later. Some researchers have proposed an elegant alternative, using the extremely precise, extremely regular pulses from spinning neutron stars, called pulsars, as a kind of cosmic lighthouse network. Comparing the timing of pulses from several known pulsars can calculate a spacecraft's position with remarkable accuracy, regardless of how far it's traveled from Earth. NASA has already tested an early version of this idea using X-ray detectors aboard the International Space Station, successfully demonstrating that pulsar-based navigation works in principle. Turning it into a fully autonomous system reliable enough to guide a starship across decades without any human oversight remains a considerable engineering task still ahead of us. The specific technique most spacecraft use for this is called triple modular redundancy. It runs 3 identical copies of a critical computer system simultaneously, comparing their outputs against each other continuously. If a cosmic ray flips a bit in one of the 3 systems, causing its output to briefly disagree with the other 2, the spacecraft's control logic simply takes the majority result. It flags the outlier system for a reset, correcting the error automatically within a fraction of a second, long before it could cause any real harm. This approach has flown successfully on numerous real spacecraft. It remains one of the most reliable, well-proven techniques for keeping computers functional in a radiation-heavy environment. A Starship would almost certainly extend this same principle further, potentially running 5, 7, or more parallel copies of its most critical control systems. It would accept the added mass and power cost for a good reason. A single uncorrected computer error at the wrong moment could mean the difference between a successful arrival and a ship that silently goes quiet somewhere between the stars. Data storage faces a related but slightly different challenge. Every scientific measurement, every navigation log, every piece of accumulated knowledge a starship gathers across its journey has to be stored somewhere. Conventional data storage media all degrade over time, whether magnetic, optical, or solid state. It's a phenomenon sometimes called data rot or bit rot. Magnetic storage can lose its charge over years. Optical media can degrade as its reflective layer oxidizes. Even solid-state memory chips experience gradual charge leakage that can eventually corrupt stored information if it isn't periodically refreshed and rewritten. Cosmic radiation makes this considerably worse. The same single event upsets that can disrupt an active computer calculation can also silently flip a bit within stored data, corrupting a file without any obvious external sign that something has gone wrong. Engineers dealing with long-term data storage in radiation-heavy environments typically rely on redundant copies stored across multiple independent systems. They combine that with error-correcting code, which can detect and automatically repair a certain number of corrupted bits. Periodic automated processes also rewrite and refresh stored data before it has a chance to degrade past the point of recovery. A starship's entire scientific and historical record depends on this quiet, unglamorous process. Everything learned across a voyage lasting generations has to work correctly every single day of the mission, with no possibility of sending a backup copy home until the ship is close enough for a meaningful transmission. There's a small but telling real-world example of this exact trade-off already flying through space right now. Both Pioneer probes carry a small engraved metal plaque. Both Voyager probes carry a golden phonograph record. These are physical, analog objects. They were designed specifically to survive far longer than any electronic storage medium could, because their designers understood that anything relying on active electronics would eventually stop working long before the spacecraft itself physically degraded. Carl Sagan and the team who designed the Voyager record chose gold-plated copper specifically for its exceptional resistance to corrosion and micrometeoroid erosion. They reasoned that the record could plausibly remain readable for hundreds of millions of years, vastly longer than the spacecraft's power source, its computers, or any of its electronic systems could ever hope to last. It's a striking illustration of the same principle we've circled back to throughout tonight's discussion. The physical structure of a well-built spacecraft can genuinely outlast every active system aboard it by an almost unimaginable margin. And sometimes, the most reliable way to preserve something for the truly long term isn't a clever piece of electronics at all. It's a simple, physically durable object that doesn't need power, software, or maintenance to keep working. Beyond electronics, cosmic radiation slowly damages the metal and composite materials that make up the ship's structure itself. This process, called radiation embrittlement, occurs because high-energy particles knock atoms out of their normal positions within a material's crystal structure, creating tiny defects. Over years and decades, these defects accumulate. Metal that was once flexible and resistant to cracking becomes progressively more brittle. It becomes more prone to fracturing under stress that it would have easily handled when the ship was new. This is a well-documented phenomenon in nuclear reactor engineering here on Earth, where reactor vessel walls slowly embrittle from decades of neutron bombardment. A starship's hull, exposed to cosmic radiation for far longer than any reactor vessel, would face the same slow degradation, just from a different radiation source. Even the ship's sensors and cameras aren't immune to this slow radiation damage. Every camera used in real spacecraft, including the detectors aboard the Hubble Space Telescope and the Kepler Space Telescope, uses light-sensitive silicon components that accumulate physical damage from cosmic ray strikes over time. That gradually increases background noise and creates small, defective pixels that no longer respond correctly to incoming light. Engineers monitoring Kepler's photometer, for instance, tracked a slow, measurable increase in this kind of sensor noise across its mission. It required increasingly sophisticated data processing techniques on the ground just to extract clean scientific results from an instrument that was quietly degrading year after year despite otherwise functioning normally. A starship's navigation cameras, star trackers, and any scientific instruments it carries would face this same slow accumulation of sensor damage throughout a multi-decade voyage. Even systems that appear to be working perfectly can be quietly losing precision and reliability well before they show any obvious outward sign of failure. Temperature adds another layer of stress on top of all this. It's one that gets worse, not better, as the ship's power source ages. Deep interstellar space sits at a background temperature of roughly 455 degrees Fahrenheit or negative 270.5 degrees Celsius. That's just a few degrees above absolute zero, warmed only faintly by the cosmic microwave background left over from the early universe. Anything on a starship that isn't actively heated will eventually settle toward that temperature. Active heating requires power. That's the same power that's already being rationed between propulsion, life support, radiation shielding, and communications. As a ship's reactor or radioisotope generator slowly declines in output over the decades, engineers have to make increasingly difficult choices about which systems still get heated and which are allowed to drift colder. It's exactly what flight controllers have already had to do with the aging Voyager probes, selectively powering down heaters for individual instruments to preserve enough energy for the spacecraft's essential core systems. A component allowed to cool too far can become brittle. It can develop stress fractures as different materials contract at different rates. It can simply stop functioning altogether if its electronics were never designed to operate at such extreme cold. Thermal management, in other words, isn't a separate problem from the power problem. It's a direct symptom of it, and it gets measurably worse with every passing year of the voyage. Real measurements back this up. The Curiosity rover has been operating on the surface of Mars since 2012, using a radioisotope power source similar in principle to the ones aboard Voyager. It carries an instrument called the Radiation Assessment Detector, built specifically to measure the radiation environment it experiences, both during its transit to Mars and on the planet's surface. Data from that instrument confirms something important. The radiation dose received during the roughly 8-month cruise to Mars, largely unprotected by any planetary magnetic field, was considerably higher than the dose measured on the Martian surface itself, where at least a thin atmosphere provides some additional shielding. That difference, measured directly rather than merely estimated, gives engineers real, hard data points. They can use it to calibrate their models. It shows what a starship would experience during years or decades spent entirely in the open radiation environment of deep space, with no planetary body nearby to offer even that partial protection. Shielding against this radiation is possible, but it's expensive in every sense that matters to a spacecraft designer. Galactic cosmic rays are mostly protons and heavier atomic nuclei accelerated to enormous speeds. Blocking them effectively requires mass, specifically mass rich in hydrogen atoms, because hydrogen nuclei are close in size to the incoming particles and absorb their energy more efficiently than heavier elements do. This is why materials like water, liquid hydrogen, and polyethylene plastic are consistently proposed as radiation shielding, rather than dense metals like lead. Lead can actually make the problem worse in some cases. When a high-energy particle slams into a heavy atomic nucleus, it can shatter it into a spray of lower energy but still dangerous fragments, a cascade sometimes called a spallation shower. Real spacecraft and space stations already deal with a milder version of this problem. Astronauts aboard the International Space Station, protected by both the station's hull and a significant portion of Earth's magnetic field, still absorb measurably more radiation than people on the surface. Mission planners already treat cumulative radiation exposure as one of the hard limits on how long any single astronaut can safely serve aboard the station. A starship traveling through interstellar space has no planetary magnetic field to hide behind at all, only whatever shielding it carries with it. That means the radiation environment it faces is significantly harsher than anything astronauts have experienced so far, even during multi-month stays in orbit. Some proposed Starship designs try to solve this the way Earth itself does, by generating an artificial magnetic field around the ship using superconducting coils. That effectively creates a miniature magnetosphere that deflects charged particles before they ever reach the hull. This is genuinely promising in theory, and small-scale versions of the concept have been tested in laboratory settings. But scaling a magnetic shield up to protect an entire Starship for decades introduces its own long-term reliability problem. The superconducting magnets themselves need to be kept at extremely low temperatures, and they need a continuous, uninterrupted power supply for the entire voyage. Lose power to the magnetic shield for even a short period, and the ship is suddenly exposed to the full, unfiltered radiation environment of interstellar space, with no way to make up for the missed protection later. Every proposed solution to the radiation problem, whether physical shielding or magnetic deflection, ultimately traces back to the same two limiting resources every other system on the ship depends on as well: mass and power. Now, consider the power source, because nothing else on the ship matters if the power runs out. Most serious interstellar Starship concepts rely on some form of nuclear power. That means either fission reactors, radioisotope generators, or, in more advanced concepts, fusion reactors that also double as the primary propulsion system. We already have real-world data on how these systems age because we've flown them. The Voyager probes, launched in the 1970s, carry radioisotope thermoelectric generators that convert the heat from decaying plutonium into electricity. These generators have been slowly losing power for decades, at a predictable and well-understood rate, losing roughly 4 watts of electrical output every year. By the 2020s, both Voyager probes had lost enough power that mission engineers had to start shutting down onboard instruments, one by one, just to keep the spacecraft's core systems and communications alive. Voyager 1 and Voyager 2 are expected to lose the last of their usable power sometime in the mid-2030s, roughly 60 years after launch. The radioactive fuel inside those generators, plutonium-238, decays with a half-life of about 87.7 years. That means the heat output, and therefore the electrical output, declines on a predictable curve for as long as the mission lasts. This isn't a malfunction. It's the fuel itself simply following the laws of nuclear physics. And engineers know the decline rate precisely enough to plan missions around it decades in advance. The practical problem is that plutonium-238 is also extremely difficult to produce, requiring specialized nuclear reactors and processing facilities. Global production has been scarce enough that NASA spent years in the 2000s and 2010s working to restart domestic production, just to guarantee enough fuel for future deep space missions. A Starship relying on this same technology would face a hard ceiling on how much power it could ever generate from radioisotope decay alone, regardless of how well engineered the rest of the ship might be. There's only so much of this material available, and no way to add more once the ship has launched. That number, 60 years, is instructive. It represents the practical outer limit of what a radioisotope power source can provide with current technology, and it's already shorter than many proposed interstellar voyages. A ship using fission reactors would fare somewhat better, since fission fuel can be loaded in far larger quantities and reactors can be throttled up or down as needed. But fission reactors carry their own long-term risks: neutron embrittlement of the reactor's internal components, gradual buildup of fission products that interfere with the reaction. The sheer engineering challenge of keeping a nuclear reactor running reliably, unattended, for decades, without a maintenance crew. Fusion reactors, if we ever perfect them, would offer far more energy from far less fuel. But fusion has been a promising future technology for longer than most people have been alive. Even optimistic engineering studies assume fusion-powered starships would still need extensive onboard maintenance systems, robotic repair units, and enormous redundancy just to keep the reaction stable across a multi-decade cruise. Most serious nuclear-powered Starship proposals also avoid relying on a single reactor entirely. For exactly the same reason, a large aircraft carries more than one engine. Multiple, smaller, independent reactor units, rather than one large central reactor, mean that a fault developing in any single unit doesn't threaten the ship's entire power supply at once. That fault might come from accumulated neutron embrittlement, a fuel handling problem, or a control system failure. A damaged reactor can potentially be shut down, isolated, and either repaired using onboard manufacturing capability or simply left offline, while the remaining units continue supplying power at a reduced but still survivable level. This distributed approach costs some efficiency compared to a single large reactor, since smaller reactors are generally somewhat less efficient per unit of mass than one larger unit would be. But it trades that efficiency for exactly the kind of graceful degradation that's shown up again and again throughout tonight's discussion. It's a system designed from the outset to keep functioning, even in a reduced state, rather than a system that works perfectly until the single moment it doesn't. Small fission reactors designed for space use, like the Kilopower project tested by NASA in the 2010s, offer a real alternative. They use a solid uranium core, roughly the size of a paper towel roll, to generate tens of kilowatts of power for a decade or more, without the steep decay curve of a radioisotope generator. Scaling that concept up to power an entire Starship for a century-long voyage is theoretically possible. But it introduces its own long-term aging problem. The metal components inside a working nuclear reactor are constantly bombarded by neutrons, gradually embrittling in much the same way the ship's outer hull embrittles from cosmic radiation, just from a more intense and more localized source. Reactor engineers on Earth already design around this by periodically replacing the most heavily irradiated components during scheduled maintenance outages. A Starship crew, human or robotic, would need to replicate that without any outside support, using onboard manufacturing to fabricate fresh reactor components from stored or processed raw material as the originals slowly wear out. Fusion reactors, if humanity ever perfects them, would sidestep many of these fuel scarcity problems. Fusion fuel, typically some combination of deuterium and helium-3, is vastly more energy-dense than fission fuel and considerably more abundant. But fusion has remained persistently difficult to achieve in a stable, sustained, net positive way, even here on Earth. Massive facilities like ITER in France have spent decades and enormous budgets working toward that goal, without yet achieving continuous power production. A fusion reactor compact and reliable enough to power a Starship for a 100-year voyage doesn't exist yet, even on paper, in a fully solved form. Most serious mission studies treat it as a future capability rather than something available today. Even once fusion power is achieved, keeping a fusion reaction stable and unattended for a century remains one of the single largest open questions in the entire field of interstellar mission design. It would need the kind of large-scale support infrastructure and highly trained engineering teams that current experimental reactors require, but without any of the people. Antimatter propulsion is sometimes floated as the ultimate long-term power source, because even a small quantity releases an enormous amount of energy when it meets ordinary matter. It introduces perhaps the single hardest containment problem of any proposed Starship technology. Antimatter has to be held suspended in a vacuum using magnetic fields, never allowed to touch the walls of its container. Contact means immediate annihilation and the release of high-energy radiation strong enough to damage the very systems meant to contain it. Humanity has produced antimatter in particle accelerators, but only in quantities measured in nanograms, and only for extremely short storage durations, measured in minutes, using current magnetic trap technology. Storing a useful quantity of antimatter safely for a journey lasting decades would need a containment system with zero tolerance for failure. That remains firmly in the realm of theoretical physics rather than practical engineering for the foreseeable future. The containment reliability problem is simply much harder than the reliability problems facing fission or even fusion power. Propellant presents its own quiet crisis, one that unfolds slowly but relentlessly. Any Starship using conventional chemical or nuclear thermal propulsion needs to carry propellant. Much of the most efficient propellant, liquid hydrogen in particular, is cryogenic, meaning it must be kept at extremely low temperatures to remain liquid. No insulation is perfect. Even the best multi-layer insulation systems used on spacecraft today allow a small amount of heat to leak in. That causes the cryogenic propellant to slowly boil off into gas, which has to be vented or used before it builds dangerous pressure. This is a solved problem for missions lasting months or a few years. It becomes a much harder problem across decades. Engineers have proposed active refrigeration systems, essentially onboard freezers that continuously recool the propellant. But those systems require power, moving parts, and long-term reliability of their own. That's yet another system that has to survive the entire journey without failing. Real spacecraft have already demonstrated just how persistent this boil-off problem is, even over comparatively short timeframes. Upper-stage rockets using liquid hydrogen, like the Centaur stage, are designed for missions lasting hours to days. Even over that short window, engineers have to carefully account for propellant lost to boil off before the stage ever fires. Longer duration missions carrying cryogenic propellant, including proposals for nuclear thermal rockets intended for crewed Mars missions, have driven serious research into what's called zero boil-off technology. It uses active cryocoolers to intercept incoming heat before it ever reaches the propellant tank. These systems have been tested on the ground and in limited orbital demonstrations. But maintaining zero boil-off performance continuously for years, let alone decades, remains unproven at any meaningful scale. Every additional year of required cryogenic storage multiplies the engineering burden on a Starship's thermal management systems. This is why many serious interstellar concepts lean toward propulsion methods that avoid carrying huge amounts of propellant altogether. Fusion ramjets, theoretically, scoop up interstellar hydrogen as fuel during the journey. They sidestep the boil-off problem, but introduce enormous engineering challenges of their own, including the need for a magnetic scoop hundreds of miles across. Laser-propelled sails, like those proposed for breakthrough Starship, carry no propellant at all after the initial acceleration phase. But they trade that advantage for extreme vulnerability to the dust erosion problem we already discussed, since a thin sail offers far less protection than a thick hull. Real-world experience with solar sails, though still limited, offers a preview of how this plays out. Japan's Icaros mission, launched in 2010, successfully deployed and flew using an extremely thin polymer sail, only a few thousandths of an inch thick, that demonstrated that the basic concept works. It also confirmed just how vulnerable such a thin membrane is to the same dust and radiation exposure every other part of a Starship has to contend with. There's just far less material available to absorb the damage before something critical tears or punctures. A laser-propelled interstellar sail, thinner still and built purely for minimum mass, would face this vulnerability in its most extreme form. It would need to survive years of dust erosion and radiation exposure using a structure that might be only a few atoms thick in places. That's part of why some proposed designs favor a sail made of engineered materials like graphene or specialized dielectric films. They're chosen specifically for their resistance to both radiation damage and micropuncture, rather than the simpler polymer films used on early demonstration missions like Icaros. The magnetic scoop required for a fusion ramjet remains almost entirely theoretical. It would need to be hundreds of miles across, generating a stable magnetic field for decades without failure. Smaller-scale relatives of the idea have been tested, though. NASA researchers experimented with a concept called mini-magnetospheric plasma propulsion in the early 2000s. They created a small artificial magnetic bubble around a spacecraft model to see whether it could effectively deflect and interact with the solar wind for propulsion purposes. The tests demonstrated the basic physics works at a small scale, but scaling that same magnetic field generation up is a different matter. It would need to both propel a Starship and collect usable fusion fuel from the sparse interstellar medium, while remaining reliable for the multi-decade duration of an actual voyage. That represents an engineering leap considerably beyond anything demonstrated so far. That's part of why fusion ramjets remain one of the more speculative entries on the long list of proposed Starship propulsion methods. Life support, for any crude version of a Starship, adds an entirely different category of long-term failure points. A closed-loop life support system has to recycle air, water, and waste with extraordinarily high efficiency because there's no resupply ship coming. The International Space Station, which has been continuously staffed since the year 2000, gives us real data here. And it isn't entirely reassuring for a decades-long voyage. Even with regular maintenance, regular replacement parts flown up from Earth, and a rotating crew of engineers actively monitoring every system, the station's life support hardware still experiences frequent breakdowns. Water recovery systems clog. Oxygen generators fail and need replacement parts. Carbon dioxide scrubbers wear out and require periodic servicing. On a real Starship, none of those replacement parts are coming. Every filter, every pump, every valve either has to be designed to last the entire voyage, or the ship has to carry a workshop capable of manufacturing spare parts from raw materials for decades on end. The Russian space station Mir operated continuously from 1986 until it was deliberately brought down in 2001. It offers an even starker warning. It operated for 15 years with aging Soviet-era hardware. Equipment failures grew more frequent toward the end of its life, including a serious fire in 1997 and repeated failures of its oxygen-generating systems, which forced the crew to rely on backup chemical oxygen candles. ground-based experiments have tried to test closed-loop life support even further. The Biosphere, II project in Arizona, was sealed shut in 1991 with a crew of 8 living inside a fully enclosed ecological system. It ran into serious trouble within its first 2 years, as oxygen levels in the sealed structure dropped low enough to require an emergency injection of outside oxygen just to keep the crew safe. That was a direct result of unexpected microbial activity in the soil consuming oxygen faster than the enclosed plant life could replace it. A smaller, longer-running Soviet experiment called BIOS-3, conducted in Siberia starting in the 1970s, achieved somewhat more stable results with a much smaller crew and a carefully balanced mix of algae and higher plants. But even that system required periodic human intervention and never achieved full, indefinite self-sufficiency. These experiments were run under far more forgiving conditions than deep space, with rescue only a phone call away if something went seriously wrong. Even so, they still struggled to maintain stable, closed-loop life support for more than a couple of years at a time. A Starship attempting the same feat for decades, with no possibility of outside rescue at all, would need life support technology considerably more advanced and considerably more thoroughly tested than anything humanity has achieved so far. Growing food adds yet another layer to the same closed-loop challenge. Plants aboard a Starship would almost certainly rely on artificial lighting rather than sunlight. Since most of a multi-decade voyage takes place far from any star bright enough to support meaningful plant growth. That means the ship's food supply becomes directly dependent on the reliability of its lighting systems and the electrical power feeding them. LED grow lights, the technology most current closed agriculture research relies on, have genuinely long operational lifespans compared to older lighting technology, often rated for tens of thousands of hours of use. But tens of thousands of hours is still only a handful of years running continuously. A multi-decade voyage would need a steady, ongoing supply of replacement components produced on board to keep every growing module lit and functioning. Add in the challenges of maintaining healthy soil or hydroponic nutrient balances, preventing crop disease in a sealed environment with no fresh outside air, and preserving genetic diversity in seed stocks across multiple plantings over decades. Food production becomes one of the quieter but most persistent, long-term survival challenges facing any crewed starship. It's closely tied to, and just as fragile as, every other system keeping the ship's occupants alive. Medical supplies present a similarly quiet but persistent problem for any crewed voyage. Most pharmaceuticals have a defined shelf life, often just a few years, after which their chemical structure begins to break down and their effectiveness can no longer be guaranteed. That's a limitation, driven by ordinary chemistry rather than anything specific to space travel. A generation ship crew facing a medical emergency decades into the voyage couldn't simply rely on medicine packed before launch. It would need onboard pharmaceutical manufacturing capability, similar in spirit to the mechanical manufacturing already discussed for spare parts, capable of synthesizing at least the most critical medications from stored raw chemical precursors as needed. That beats, depending on a finite stockpile that would have expired long before the voyage was even half complete. Researchers studying long-duration spaceflight, including work done in preparation for eventual crewed Mars missions, have already begun exploring compact pharmaceutical synthesis technology for exactly this reason. Even a journey measured in years, let alone decades, outlasts the practical shelf life of most medicine a crew could realistically carry with them from the start. This points to one of the most important concepts in long-duration Starship design, something engineers call graceful degradation, paired with onboard manufacturing. A ship intended to survive a journey lasting many decades likely wouldn't rely purely on parts built before launch. It would need extensive robotic manufacturing capability, essentially a self-contained factory able to produce replacement components, seals, and even structural elements from stored or recycled raw material. This sounds almost like science fiction, but versions of this technology already exist in early form, from three-dimensional metal printers used in industry today to experimental systems tested for potential use in orbit. The challenge is scaling this up. A ship would need to genuinely manufacture anything it might need across a 100-year voyage, using only the raw materials it carries or can somehow gather along the way. This kind of prioritization already happens in a real, ongoing way with the Voyager mission today. Flight controllers at the Jet Propulsion Laboratory hold regular reviews, specifically to decide which instrument or heater to power down next as the spacecraft's dwindling energy budget shrinks. They weigh the scientific value of each system, still running against the electricity it consumes. Then they choose, deliberately and carefully, what to sacrifice in order to keep the spacecraft's core systems and its ability to communicate alive for a few more years. It's a genuinely human process. Engineers making judgment calls about a machine that's been flying for longer than many of them have been alive. It offers a real preview of the kind of ongoing, unglamorous decision-making a Starship crew, or the automated systems managing an uncrewed probe, would need to keep making continuously across a voyage lasting decades. They would constantly triage a slowly shrinking pool of available power and resources among competing systems that all matter, just not equally, and not all at the same time. Mechanical wear compounds all of these problems. Anything with moving parts wears down through simple friction, even when lubricated. Pumps, valves, gyroscopes, actuators, bearings, all of it. In the vacuum of space, many conventional lubricants slowly evaporate or degrade under radiation exposure. That leaves moving parts to grind against each other with increasing friction over time. Spacecraft engineers already deal with this on a smaller scale. Reaction wheels, used to control a spacecraft's orientation, have failed on multiple real missions after years of continuous use. The Kepler Space Telescope lost the use of 2 of its 4 reaction wheels after roughly 4 years of operation. That forced engineers to develop a creative workaround just to keep the telescope pointed accurately. A Starship would rely on thousands of moving mechanical components, far more than any single robotic probe. Each one represents another potential failure point across a mission lasting orders of magnitude, longer than anything we've flown before. Other missions tell a similar story. The Dawn spacecraft used efficient ion engines to visit the asteroids Vesta and Ceres. It eventually ran out of the hydrazine fuel needed to keep its antenna pointed at Earth and its solar panels pointed at the Sun, ending its mission in 2018. Its ion engines didn't fail. A completely different, comparatively mundane system did, its attitude control propellant, simply running dry after 11 years of operation. The Cassini spacecraft spent 13 years studying Saturn and experienced gradual degradation across multiple instruments and thrusters throughout its mission. Mission planners ultimately chose to deliberately plunge it into Saturn's atmosphere in 2017, while it could still be reliably controlled. The alternative was risking losing control of an aging spacecraft entirely and potentially contaminating one of Saturn's moons. Even the Hubble Space Telescope, which benefited from multiple servicing missions by astronauts, something a true Starship in deep space could never receive, has needed repeated gyroscope replacements over its multi-decade lifetime. Each individual gyroscope has historically lasted somewhere between a few years and about a decade before wearing out. Every one of these examples involves a spacecraft in a relatively gentle environment compared to true interstellar space. Less radiation, less relative velocity dust erosion, and in most cases, at least the theoretical possibility of a servicing mission. A Starship built for a genuine interstellar voyage doesn't have that luxury. Every one of its moving mechanical systems would need to either last far longer than any of these examples or be replaceable using onboard manufacturing, with no servicing mission ever available to help. Radiation compounds the mechanical wear problem in a way that's easy to overlook. Most conventional lubricants are organic compounds. Organic molecules are exactly the kind of material galactic cosmic rays are especially effective at breaking apart, snapping long polymer chains into shorter, less effective fragments over years of continuous exposure. A lubricant that performs perfectly during ground testing and even during the first several years of a mission can slowly thicken, degrade, or lose its lubricating properties entirely after a decade or two of accumulated radiation exposure. That happens exactly when the ship needs its moving parts to keep functioning smoothly the most. Engineers working on long-duration spacecraft have increasingly turned to dry lubricants, thin coatings of materials like molybdenum disulfide that don't rely on organic chemistry at all. They hold up considerably better under sustained radiation exposure than traditional oil-based lubricants, even though they generally don't perform quite as well under heavy mechanical load. It's another example of the same pattern that shows up throughout Starship engineering. A solution to one problem, radiation resistance, comes at the cost of performance in another area, mechanical efficiency. That forces designers to carefully balance trade-offs across every single component, rather than optimizing any one system in isolation. Airlocks and docking mechanisms. If the ship ever needs to use them for external inspection or repair work, add one more category of wear to track. Every time a hatch seals and unseals, its gasket material compresses and releases, gradually losing some of its elasticity with each cycle. It's the same basic aging process affecting every other seal on the ship, just concentrated on a component that gets used repeatedly by design, rather than remaining sealed for the entire voyage. Real spacecraft already track this kind of wear carefully. The hatches and docking mechanisms aboard the International Space Station undergo scheduled inspection and periodic seal replacement, precisely because engineers know from experience that repeated use accelerates this kind of gradual degradation. A Starship, relying on regular external maintenance, sending robotic or human crews outside the hull to inspect shielding or repair damaged sensors, would need a generous supply of replacement seals and gaskets for its airlocks specifically. They would need to treat them as a consumable resource, manufactured and replaced throughout the voyage, rather than a fixed component expected to last untouched from launch to arrival. Structural fatigue is the slowest of these threats, but in some ways the most inevitable. Every time a ship's hull heats up in sunlight and cools in shadow, the metal and composite structure expands and contracts by tiny amounts. Same thing every time. Internal systems cycle on and off, or propulsion systems fire and shut down. Repeated enough times, this thermal cycling causes microscopic cracks to form and slowly grow, a process engineers call fatigue failure. It's the same phenomenon that eventually grounds aging aircraft here on Earth, even ones that have never suffered a dramatic accident. It happens simply because their airframes have accumulated too many pressurization cycles over their operational lifetime. A Starship on a multi-decade voyage would experience an enormous number of thermal and stress cycles. Unlike an aircraft, it can't be grounded for inspection and repair at the first sign of trouble. Engineers design around this with generous safety margins and careful material selection. But every safety margin has a limit, and a long enough voyage will eventually test it. Cold itself, independent of radiation, causes its own version of embrittlement. Most metals have what materials scientists call a ductile to brittle transition temperature. That's a threshold below which a metal that would normally bend or deform under stress instead cracks suddenly and catastrophically, with almost no warning beforehand. This is a well-known hazard in cold weather engineering here on Earth. It was a contributing factor in several ship hull failures during the frigid North Atlantic winters of the mid-20th century. It remains a serious design consideration for any structure expected to operate in extreme cold. A Starship hull, especially any section not actively heated to conserve dwindling power, could drift toward temperatures far colder than any structure has ever been designed to withstand on Earth. Engineers selecting hull materials have to account for how those materials behave not just under radiation and repeated stress, but at temperatures within a few dozen degrees of absolute zero. They choose alloys specifically engineered to remain ductile, even in that extreme cold, rather than the conventional steel and aluminum alloys used in most terrestrial and near-Earth engineering. Choosing the actual material for a Starship's hull involves balancing several of these threats against each other simultaneously, and there's no single obviously correct answer. Titanium alloys offer excellent strength for their weight and hold up well against fatigue, but they're expensive to produce and machine in the quantities a full-size Starship would require. Aluminum alloys are lighter and cheaper, with a long flight heritage from decades of conventional spacecraft. But they're generally more vulnerable to the kind of radiation, embrittlement, and fatigue cracking we've discussed tonight than some of the more exotic alloys developed more recently. Advanced steel and nickel-based superalloys, similar to materials used in jet engine turbines here on Earth, offer excellent resistance to both fatigue and high-temperature stress. But they add significant mass compared to lighter alternatives. Most serious Starship hull proposals end up recommending a hybrid approach, using different materials for different sections of the ship, depending on what threat that particular section faces most. That could mean a heavier, more radiation-resistant alloy for the leading shield and outer hull, and lighter, more efficient materials for internal structural elements that face less direct exposure to dust impacts and cosmic radiation. Composite materials, increasingly favored in spacecraft design because they offer excellent strength for their weight, introduce a slightly different version of the same problem. Metal tends to fail through a gradual, somewhat predictable buildup of cracks. Composite materials made from carbon fiber embedded in resin fail differently, through a process called delamination. The individual layers of the material slowly separate from each other due to repeated stress, thermal cycling, and radiation exposure to the resin binding them together. This kind of damage can be extremely difficult to detect from the outside. A composite panel can look completely intact on its surface, while its internal layers have already begun separating, only revealing the full extent of the damage under a sudden significant load. Engineers studying long-duration, composite performance for aerospace applications have found that ultraviolet exposure and radiation both accelerate resin degradation considerably. That's a genuine concern for any Starship hull relying heavily on composite materials for a voyage measured in decades rather than years. This is part of why many long-duration Starship concepts favor metal alloys or metal composite hybrid structures for their primary structural elements. They reserve lighter composite materials for less critical, more easily inspected or replaceable components. Putting rough numbers on each of these categories helps make the overall picture concrete. A well-built structural hull, protected by adequate shielding and built from radiation-resistant alloys, could plausibly remain physically sound for many centuries, based on what we've already observed from spacecraft like the Pioneer and Voyager probes. A radioisotope power source, using current technology, reliably provides useful electricity for somewhere in the range of 50 to 70 years before declining below a useful threshold. A well-designed fission reactor with proper redundancy and periodic component replacement could plausibly extend that considerably further, perhaps into the range of 1 to several centuries. That's provided the ship carries the manufacturing capability to keep replacing irradiated reactor components as they wear out. Mechanical systems without any repair capability tend to show real degradation somewhere in the range of 20 to 50 years. That's based on the lifespans observed in reaction wheels, gyroscopes, and propulsion hardware across real missions flown so far. Onboard manufacturing and robotic maintenance could extend that range considerably if the ship carries enough raw material and spare capacity to keep producing new components indefinitely. Radiation-hardened electronics, combined with heavy redundancy and error-correcting systems, can realistically be expected to remain functional across a similar multi-decade to multi-century range. Again, contingent on continuous power availability and periodic component replacement. Line all of these ranges up together, and the picture that emerges is one where the ship's structure is almost never the limiting factor. Power, mechanical wear, and the ship's overall manufacturing and repair capability collectively determine just how long the vessel can keep every other system alive alongside it. So, if we line all of these failure modes up, which one wins first? The honest answer is that power is usually the limiting factor. That's based on everything we currently understand about materials, power systems, and long-duration spaceflight. Mechanical and life support systems follow closely behind. The structural hull itself is typically the most durable component, at least on the multi-decade timescales we're discussing. This matches what we've already observed with real spacecraft. The Voyager probe's structural hull is, as far as engineers can tell, still perfectly intact after roughly 5 decades in the vacuum of space. What's failing isn't the metal skin of the spacecraft. It's the power source slowly decaying. It's the fuel for attitude control thrusters slowly running low. It's individual instruments failing one by one as their specific components age past their design life. This gives us a genuinely useful benchmark. It also matters enormously what kind of mission we're actually talking about, because not every Starship needs to survive the same length of time to be considered a success. A robotic probe designed for a single flyby of a nearby star system only needs its critical systems to survive long enough to reach the destination and transmit its findings. That could mean just a few decades, depending on the target. A one-way colonization vessel needs more. It has to decelerate, enter orbit around a distant world, and support a crew capable of eventually stepping onto a new planet. That means everything has to keep working for the entire outbound cruise, plus a meaningful deceleration and arrival phase. That likely extends the required survival window considerably. A true generation ship, one intended to serve as a permanent, self-sufficient home for multiple generations before anyone aboard ever expects to arrive anywhere, faces the longest and most demanding survival requirement of all. It needs not just decades, but centuries of reliable function from nearly every system we've discussed tonight, simultaneously, without interruption. This pattern has played out across several real missions, and the consistency is striking. Pioneer 10, launched in 1972, it kept transmitting a faint signal until 2003, roughly 31 years, before its radioisotope power finally dropped below the threshold needed to communicate with Earth. Its structural hull almost certainly remains completely intact today, tumbling silently somewhere beyond the outer solar system with no power left to say so. New Horizons launched in 2006 with a more modern radioisotope generator. It's expected to have enough power to continue operating scientific instruments into the 2030s, roughly 3 decades after launch, following the same predictable decay curve as its predecessors. In every case, across nearly 5 decades of real deep space missions, the pattern holds. The physical structure of these spacecraft outlasts their power systems by a wide margin. Their power systems, in turn, outlast the mission's ability to keep every individual instrument running simultaneously. Every one of these real missions, even the ones that have already gone silent, continues to teach engineers something valuable long after their science instruments stopped returning new data. Pioneer 10's slow fade into silence. New Horizons' carefully managed power budget. Voyager's ongoing instrument shutdowns. All of it becomes a permanent part of the engineering record, studied and referenced by anyone designing the next generation of long-duration spacecraft. In a very real sense, humanity has already been running a decades-long, unplanned experiment in exactly the question we started with tonight. How long can a real spacecraft actually survive out there? Every year that passes adds another data point to an answer that keeps getting a little more precise. With 1970s-era technology, using a radioisotope generator with no possibility of refueling, a real spacecraft has managed to survive and remain at least partially functional for around 50 years. Its structure could likely remain physically intact for centuries beyond that, long after its power and instruments have gone silent. A more advanced Starship could plausibly extend functional survival well beyond that 50-year mark. Modern materials, active thermal management, redundant fission or fusion power, onboard manufacturing capability for spare parts that could reach into the range of 1 to several centuries, depending entirely on how much redundancy and self-repair capacity its designers were willing to build in. There's another system to consider here, one that's easy to overlook because it doesn't keep anyone alive directly, and that's communication. A starship traveling toward another star system, or even a robotic probe continuing on past our own solar system, needs a way to send information home. The physics of that problem gets harder the farther away the ship travels. Radio signal strength weakens, according to the inverse square law. A signal that's easily detectable at 10 light-years away becomes far fainter at 20, and fainter still beyond that. Voyager 1 is now well over 15 billion miles from Earth. By the time its signal reaches the Deep Space Network's giant dish antennas, it's so faint that engineers have described it as roughly 20 billion times weaker than the power of a modern digital wristwatch battery. Every year, as the ship travels farther and its power source continues to decay, that already faint signal grows fainter still. That forces mission engineers to continually refine how they extract usable data from what's essentially a whisper arriving from the edge of the solar system. A true interstellar starship, traveling not just past the edge of the solar system, but across multiple light years to another star, would face this same problem, magnified enormously. It would need an extraordinarily powerful transmitter, an enormous receiving antenna back on Earth, or, more likely, both. That's just to maintain any communication at all across the final years of its voyage, long after its power source has declined to a fraction of what it started with. But there's a difference between the ship surviving and the ship remaining fully functional. That distinction matters enormously for anyone planning to actually travel inside it. A structurally intact hull, drifting silently with a dead reactor and failed life support, isn't a surviving starship in any meaningful sense. It's a very well-preserved tomb. For a crewed interstellar voyage to actually succeed, every major system needs to remain functional simultaneously for the entire duration of the trip. Power, life support, propulsion, structure, all of them, not just the most durable one. This is why realistic starship proposals almost universally include massive redundancy, multiple independent power sources, backup life support loops that can operate even if the primary system fails completely, enough onboard repair capability to keep replacing worn components indefinitely. Reliability engineers have a useful way of thinking about this trade-off, using a measurement called mean time between failures. It's essentially a statistical estimate of how often a given component is expected to break down under normal operating conditions. A single pump with a mean time between failures of 20 years sounds reasonably durable on its own. But a starship might depend on hundreds or even thousands of individually critical pumps, valves, sensors, and actuators. The combined probability that at least one of them fails in any given year climbs quickly once you're managing that many components simultaneously. This is precisely why redundancy matters so much more in spacecraft design than it does in most everyday engineering. Doubling or tripling a critical system doesn't just provide a backup in case of an obvious catastrophic failure. It dramatically improves the statistical odds that the ship as a whole keeps functioning. A single unaddressed failure could otherwise cascade into something far more serious, especially if it's left unrepaired for years because no technician can reach it. Engineers designing real spacecraft already build extensive redundancy into critical systems for exactly this reason. A starship, intended to function for decades or centuries, would need to push that redundancy further than any spacecraft humanity has built so far. That likely means combining it with predictive monitoring systems, capable of flagging a component, showing early signs of wear long before it actually fails completely. Even with all of that redundancy, there's a hard ceiling imposed by something engineers can't design around, and that's the total mass the ship can carry. Every spare part, every redundant system, every extra layer of radiation shielding adds weight. Weight directly determines how much propellant is needed to reach a useful cruising speed. This creates a genuine engineering trade-off at the heart of every serious starship design. Build in enough redundancy to survive a 100-year voyage, and the ship becomes massive. Reaching even a modest fraction of light speed then requires an almost absurd amount of propellant, or an almost absurdly powerful and long-lived propulsion system. Build a lighter, faster ship instead, and you sacrifice some of the redundancy that would let it survive the trip in one working piece. This trade-off is why so many serious mission studies conclude that the most realistic first interstellar missions probably won't be crewed at all. They'll be small, relatively simple, robotic probes, prioritizing speed and simplicity over the kind of extreme longevity a crewed generation ship would require. The underlying reason mass matters so much traces back to a piece of physics known as the rocket equation, first worked out by the Russian scientist Konstantin Tsiolkovsky in the early 1900s. In simple terms, it describes how the amount of propellant a ship needs grows exponentially, not just proportionally, as the desired final speed increases. Small increases in a ship's target velocity demand disproportionately large increases in the propellant it has to carry. Add extra mass anywhere on the ship, whether it's radiation shielding, redundant life support hardware, or spare parts for robotic repair systems. That added mass has to be paid for somewhere. It's either offset by carrying substantially more propellant, which adds still more mass in a compounding cycle, or by accepting a slower final cruising speed and therefore a longer total voyage. This single piece of 19th and early 20th century mathematics is arguably the single most important constraint shaping every serious Starship design that's ever been proposed. It's the fundamental reason engineers can't simply add unlimited redundancy and unlimited shielding to solve every survival problem we've discussed tonight. Every gram matters, and every gram added for longevity is a gram that has to be paid for somewhere else in the ship's overall performance. If we're talking specifically about uncrewed robotic starships, the calculus shifts considerably in favor of long-term survival, because you remove the enormous burden of keeping humans alive. No air to recycle, no water to purify, no food to grow, no psychological toll from generations spent in a metal tube. A robotic probe still faces every threat we've discussed: radiation, erosion, power, decay, mechanical wear. But it faces them with a vastly simpler set of systems to keep running. This is part of why probes like Voyager have managed to remain at least partially operational for as long as they have. It's a strong argument for why humanity's first genuine interstellar missions will almost certainly be robotic, scouting ahead for decades or even centuries before any crewed mission ever attempts the same journey. There's something quietly striking about what actually happens after a starship's systems finally do go silent, whether that happens after 50 years or 500. Almost anything built on Earth eventually rusts, burns, or gets torn down and recycled into something else. A spacecraft that loses power in deep space doesn't really decay away in any meaningful sense afterward. There's no atmosphere to cause weathering. There's no bacteria or fungus to break down its materials. There's no gravity to pull it down onto any surface where erosion could slowly wear it apart. A starship structure would likely remain almost exactly as it was the moment its last system finally failed. It would drift silently and essentially unchanged for a length of time that dwarfs every number we've discussed tonight, plausibly for millions of years. It would quietly carry whatever remained of its mission long after everyone who built it, and everyone who ever knew about it, was gone. For a crewed generation ship specifically, one designed to carry multiple generations of people across a journey lasting centuries, the survival question becomes even more demanding. The ship itself has to function as a stable, livable world for far longer than any single human lifetime. This is where onboard manufacturing and repair capability stops being a helpful bonus and becomes an absolute requirement. A generation ship would essentially need to become self-sufficient in every meaningful sense. It would need to mine or process raw materials it carries, manufacture replacement parts for every system on board, and maintain that capability across a period longer than most nations on Earth have existed as continuous political entities. It's a genuinely staggering engineering challenge. It's also part of why many researchers who study this question believe that slower, patient, well-maintained generation ships may actually be more survivable than faster ships pushing the limits of speed and lightweight construction. A slower ship simply has more mass budget available for redundancy and repair capability. And the ship's survival in that scenario doesn't only depend on its mechanical and electrical systems. It depends on the people managing those systems, remaining organized, trained, and capable across multiple generations, who never asked to be born on a voyage between the stars. Knowledge has to be passed down carefully. The great-grandchildren of the original crew still need to understand how to repair a fusion reactor or recalibrate a life support loop, even though none of them will have ever set foot on the world their grandparents left behind. Real-world institutions here on Earth offer only a rough sense of how hard this is. Even well-documented technical knowledge tends to drift, get simplified, or get lost entirely across a few generations without deliberate, sustained effort to preserve it. That's why some generation ship proposals include redundancy beyond just their machinery. They build in redundancy in training, education, and institutional memory itself, treating the transmission of technical knowledge as seriously as the transmission of oxygen or electrical power. There's also the question of how the ship's various systems interact with each other as they age, because failures rarely happen in isolation. A slowly degrading power source doesn't just dim the lights. It reduces the energy available for radiation shielding systems, for active thermal control, for the life support loop, for the manufacturing equipment needed to produce spare parts. As power output declines, engineers on board, whether human or increasingly automated as generations pass, would likely need to make difficult choices about which systems to prioritize. It's exactly what mission controllers on Earth have had to do with the aging Voyager probes. They shut down instrument after instrument to preserve enough power for the essential core of the spacecraft to keep functioning and keep communicating with home. Researchers working on self-healing materials offer one genuinely promising path forward, even though the technology remains early stage today. Some experimental polymers and coatings, developed in laboratories over the past 2 decades, contain microscopic capsules of liquid resin embedded throughout the material. They're designed to rupture and seal a crack automatically the moment one begins to form, without any outside intervention at all. Other research explores metal alloys engineered to redistribute stress around a developing crack, effectively slowing its growth rate significantly compared to conventional metals. None of these technologies have been tested at the scale or over the time frame a real Starship would require, and most exist only in laboratory samples or small-scale demonstrations so far. But they represent exactly the kind of incremental engineering progress that would need to continue for decades before a genuinely long-lived Starship hull became achievable. A well-designed Starship of the future could plausibly extend its structural lifespan considerably beyond anything achievable with today's materials alone. That means robotic inspection systems capable of continuously scanning the ship's structure for early signs of fatigue, radiation embrittlement, or dust erosion. It also means manufacturing systems capable of producing replacement panels or components on demand. There's an obvious complication hiding inside this whole idea of robotic repair and onboard manufacturing, one that engineers studying long-duration autonomous systems take seriously. The robots doing the repairing are themselves machines. They're built from motors, joints, sensors, and actuators. All of it wears out through exactly the same friction, radiation exposure, and thermal cycling as everything else on the ship. A Starship that depends heavily on robotic maintenance. Crews needs those robots to be reliable and repairable enough to keep functioning for the entire voyage as well. That usually means designing multiple generations of maintenance robots capable of building and repairing each other, along with spare parts and manufacturing capacity dedicated specifically to keeping the repair robots themselves running. It's a genuinely recursive engineering problem. Maintenance systems that need their own maintenance. It's one of the clearest illustrations of just how deep the redundancy has to go on a voyage measured in decades or centuries rather than months. In practical terms, a Starship capable of sustaining itself this way would need something like a fully equipped, miniaturized industrial facility built into its hull. It would combine metal refining and shaping equipment with precision three-dimensional printers capable of working in metal, ceramic, and polymer materials. It would need a chemistry lab capable of synthesizing everything from lubricants to pharmaceuticals. And it would need a stockpile of raw feedstock material large enough to supply all of that manufacturing for the entire duration of the voyage. Some proposals suggest recycling as much of this raw material as possible, breaking down worn-out or obsolete components to recover usable metal and polymer stock, rather than relying solely on material carried from launch. That's essentially a continuous, closed-loop industrial economy in miniature, floating through interstellar space. It's an enormous undertaking, arguably as complex as any other single system on the ship. It illustrates just how far the concept of a Starship has to evolve beyond a simple vehicle. A genuine multi-decade or multi-century Starship isn't really a vehicle in the way we normally think about the word. It's closer to a small, self-sufficient, industrial civilization built to travel. Underneath every one of these specific engineering problems sits a much older and much more fundamental one. It's the same one that governs everything, from a cup of coffee cooling on a table to a star eventually burning through its fuel. The second law of thermodynamics states, in simple terms, that isolated systems tend toward increasing disorder over time. Energy naturally spreads out and becomes less useful unless something actively works against that tendency. A Starship is, in every meaningful sense, a tiny, isolated pocket of extraordinary order. It's a carefully organized arrangement of metal, fuel, electronics, and in some cases, living organisms. It's sent out into an environment that has no interest in preserving that order at all. Keeping a Starship functional isn't really a battle against any single threat like radiation or dust or mechanical wear. It's a continuous, active fight against entropy itself, using stored energy and careful engineering to keep pushing back against the universe's natural tendency to let everything fall apart. Every one of the systems we've discussed tonight exists purely to slow that process down for as long as possible. The shielding, the power source, the manufacturing bays, the redundant life support loops. This cascading effect is arguably the real answer to how long a Starship can survive. It's not a single number, a single point where the ship simply stops working. It's a long, slow negotiation between multiple degrading systems, each one placing more strain on the others as it weakens. Eventually, the ship can no longer maintain the minimum functionality needed to keep its crew alive. Or, in the case of a robotic probe, it can no longer maintain enough power and structural integrity to keep transmitting useful data home. Based on everything we currently understand about materials, science, nuclear power systems, and the harsh realities of the interstellar medium, here's a realistic estimate. A well-engineered robotic starship, without any crew to support, could achieve meaningful functional survival somewhere in the range of 1 to 2 centuries. The structural hull itself could potentially remain intact for far longer after that, silently drifting long after its systems have gone quiet. For a crew generation ship, built with the enormous redundancy and self-sufficiency required to keep people alive across that same span of time, the honest engineering answer is that we genuinely don't know yet. Humanity has never built or tested a closed system meant to remain fully self-sufficient for anywhere close to that long. Our best real-world analog is the International Space Station. It required constant resupply and a rotating crew of trained engineers just to remain functional for a couple of decades in low orbit. A tiny fraction of the distance and duration a real interstellar generation ship would need to endure. Everything beyond that is extrapolation, informed by physics and materials, science, but ultimately unproven until humanity actually attempts it. What we can say, with real confidence, is this. A starship, any starship, is fighting a battle against entropy from the moment it leaves home, and entropy never stops working. Radiation slowly weakens its structure. Dust slowly erodes its leading edges. Seals slowly crack. Power sources slowly decay. Moving parts slowly wear down. None of these processes can be stopped permanently, only slowed, managed, and repaired for as long as the ship has the resources and the redundancy to keep doing so. Eventually, on any long enough timescale, every one of these processes wins. The only real question engineers can answer is how long a well-designed ship can keep winning the smaller battles before it finally loses the larger war. It also helps to remember that almost none of the individual engineering problems we've covered tonight are actually unsolved in isolation. We already know how to build effective radiation shielding, even if scaling it to interstellar durations is difficult. We already know how to build layered impact shields, because the International Space Station uses one today. We already know how fission reactors age and how to design around neutron embrittlement, because nuclear engineers have been managing that exact problem in terrestrial power plants for decades. We already have early, working examples of self-healing materials, closed-loop life support, and robotic manufacturing. None of them have yet been proven at the scale or duration a genuine starship would require, though. What's missing isn't a single breakthrough discovery. It's the patient, unglamorous work of scaling dozens of individually solved problems up together. That means integrating them into one coherent system. Then, testing that system for far longer than any spacecraft humanity has built so far, to find out where the unexpected interactions between all those systems start to show up. This is precisely the kind of engineering progress that tends to happen quietly, one incremental improvement at a time, rather than through a single dramatic invention. It's exactly the kind of progress that's been steadily accumulating across aerospace, materials, science, and nuclear engineering for the better part of a century already. There's also something striking in just how much of what we know about long-term survival in space comes from missions that were never designed to last anywhere near as long as they ultimately did. The Voyager probes were built for a primary mission lasting a handful of years, a tour of the outer planets. Nobody on the original engineering team fully expected them to still be transmitting data from beyond the edge of the solar system nearly 5 decades later. That kind of unplanned longevity is genuinely encouraging for anyone thinking seriously about future starships. It emerged from careful, conservative, redundant engineering, not any specific design goal of surviving 50 years. It suggests that a spacecraft built with real engineering discipline, generous safety margins, and a healthy respect for how harsh deep space actually is, tends to outperform even the expectations of the people who built it. If that pattern holds as engineering knowledge continues to improve, the implications are exciting. A purpose-built interstellar starship, designed from the very beginning with a multi-decade or multi-century voyage in mind, rather than stumbling into unexpected longevity by accident, could plausibly exceed even the most optimistic estimates we've discussed tonight. None of this makes the challenge smaller. A starship attempting a real interstellar crossing is still fighting against physics that doesn't care how clever the engineering is. It fights against radiation that never stops arriving. It fights against dust that never stops sandblasting the leading edge of the hull. It fights against power sources that decay whether or not anyone is watching, and against the simple, patient math of entropy that eventually claims every isolated system left to itself for long enough. But it does mean the challenge is fundamentally an engineering one, not a question of physics forbidding the attempt entirely. Nothing about a multi-decade or multi-century starship voyage violates any known law of nature. It only demands an almost unreasonable level of care, redundancy, and foresight from the people designing it, applied consistently across thousands of individual components. Any one of those components could eventually become the weak link that ends the mission if it's overlooked. And that's genuinely inspiring in its own way. It means the future of interstellar travel isn't a question of finding some magic material that never wears out or some perfect system that never fails. It's a question of patient, careful, redundant engineering. It's about building ships that expect to fail in 1,000 small ways and are designed from the very beginning to repair themselves faster than the universe can wear them down. Every spacecraft we've ever flown has taught us something new about how materials behave over years and decades in the vacuum of space. And every lesson brings a real starship, one that could genuinely survive the crossing to another star, a little closer to something we could actually build. It's fair to ask why any of this matters, given that humanity hasn't built anything close to a real starship yet, and likely won't for a considerable time to come. Part of the answer is simple. Working through these problems now, carefully and honestly, using real physics and real engineering data rather than optimistic guesswork, is exactly how every genuinely difficult human achievement has ever gotten started. Every technology we rely on today, from commercial aviation to satellite communication to the spacecraft already quietly aging their way through the outer solar system, began as a set of problems that looked nearly impossible on paper. They were solved gradually, piece by piece, by people willing to take the engineering seriously long before the finished technology actually existed. Understanding exactly how a starship would fail, what would wear out first, what redundancy would actually be needed, isn't a distraction from the dream of interstellar travel. It's the necessary, unglamorous groundwork that any real attempt would eventually have to be built on. So, if someone ever asks you how long a real starship could survive out there in deep space, The honest answer isn't a single dramatic number pulled from a movie poster. It's this: long enough if we build it carefully enough, but never forever. A starship, no matter how advanced, is still a machine. And every machine is having a quiet, patient argument with the laws of physics from the moment its engines first ignite. The best we can do, the best any civilization could do, is build a ship stubborn enough to keep winning that argument for as long as the voyage demands. Thank you for joining me on this journey through the engineering realities of interstellar travel. If you found this exploration valuable, a like or subscribe helps us continue making these deep examinations of the cosmos. And remember, every spacecraft humanity has ever sent into the dark has quietly rewritten what we thought was possible. It's taught us a little more about how long metal, fuel, and ingenuity can hold together against the patient, indifferent pressure of deep space. Good night. And may the ships we one day build outlast every doubt we ever had about building them.